Hello, everyone. Tonight, let's take a quiet, unhurried journey through the Milky Way, not as a battlefield of explosions and dramatic collisions, but as a vast, ancient structure that has been patiently arranging itself for billions of years. A galaxy is not a single object you can hold in your mind all at once. It is a layered system: stars, gas, dust, dark matter, time, motion, chemistry, gravity, and the slow exchange of energy. The Milky Way is our home galaxy. It is the environment that shaped the sun, the planets, and the long chain of events that eventually led to you, listening now. And even though it feels impossibly distant, it is also intimate. The atoms in your body were forged in stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of them were cooked in stellar interiors and released into space and recycled again and again until a small part of that material became Earth. So as you settle in, you can think of this as a calm story about origins, not a loud story, not a rushed story, a steady one. Take a slow breath and imagine the Milky Way not as a picture, but as a place with regions, a place with texture, a place with a shape that only becomes clear when you zoom far, far out. From Earth, we see the Milky Way as a pale band of light across the night sky, a soft river of brightness. That glow is not a cloud, it is not mist. It is the combined light of countless distant stars, too faint and too crowded to separate with the naked eye. We live inside the galaxy's disk, so when we look along the disk's plane, we look through a long, dense corridor of stars and dust. The galaxy becomes a luminous stripe, stretched across the sky. If you have ever seen it from a dark place, far from city lights, you may remember how it looks almost textured, as if there are layers and knots. That texture is real. It comes from interstellar dust lanes, from star clouds, from clusters, from different thicknesses of the galactic disk. Even the darkness in the Milky Way is meaningful, because it often marks where dust is blocking starlight, where the galaxy's raw material gathers. The Milky Way is a spiral galaxy, more specifically, a barred spiral galaxy. That means it has a central bar-shaped region of stars, and from that bar extend spiral arms that curve outward like gentle streams. Spiral arms are not rigid structures. They are not like the arms of a toy pinwheel. They are patterns, shaped by gravity, by density waves, by the way stars and gas orbit the center at different speeds. A useful way to imagine it is to picture traffic on a highway. The cars are like stars and gas, each moving forward. A traffic jam is like a spiral arm, a region where density increases, where material slows slightly, where interactions become more likely. Cars enter the jam, pass through it, and leave it. The jam can persist as a pattern, even though the individual cars are always changing. Spiral arms can act like that, guiding gas into denser regions where it can cool, collapse, and form new stars. The Milky Way is large, but the word large doesn't do much on its own. So let's make it gentle and specific. The disk of the Milky Way is about 100,000 light years across, give or take. A light year is not a time, it is a distance. The distance light travels in 1 year. Light moves incredibly fast, about 300,000 kilometers per second. Even at that speed, it takes light a year to cross the distance we call 1 light year. So when we say the galaxy is about 100,000 light years across, we are saying that even a beam of light, the fastest messenger in the universe, needs about 100,000 years to travel from one side of the disk to the other. Our sun sits in the disk, not at the center, but in the suburbs, roughly 26,000 light years from the galactic center. We are located in a region called the Orion Arm, sometimes described as the Orion Spur, a smaller feature between two major spiral arms, the Sagittarius Arm and the Perseus Arm. In the night sky, many of the stars you see are neighbors in this local region, all orbiting the galactic center together, like leaves floating in a slow-moving, enormous whirlpool. When you imagine the galaxy's center, you might imagine something like a bright core. And yes, the central region is dense and energetic. It contains a bulge of stars, and within the deepest center, there is a supermassive black hole called Sagittarius A star. That black hole has a mass of about 4 million suns. A black hole is not a cosmic vacuum cleaner. It does not automatically swallow everything. Most things orbit it safely, just as planets orbit the Sunday. A black hole is a region where mass is compressed enough that the escape speed exceeds the speed of light. But at the distance of our solar system, Sagittarius A star is a quiet gravitational fact, part of the overall mass distribution that shapes our orbit. In the central few thousand light years of the galaxy, stars are packed more densely. There are also complex flows of gas, magnetic fields, and energetic events. But even there, much of the time, the galaxy is not a fireworks show. It is a patient system. Stars live for millions to billions of years. Gas clouds drift and collide slowly. Gravity shapes orbits with calm persistence. Now, to understand the Milky Way in a scientific way, it helps to think in components. There is the disk, a flattened region containing many of the galaxy's stars, along with much of its gas and dust, and most of its active star formation. The disk is where spiral arms are found. The disk has a thin part, where young stars and gas clouds live, and a thicker part with older stars that have more varied orbits. There is the bulge, a central swelling of stars. The bulge contains older stars on more random, more elliptical orbits, moving in different directions rather than in the tidy rotation of the disk. There is the halo, a large, roughly spherical region surrounding the disk and bulge. The halo contains old stars, globular clusters, and, most importantly, a great deal of dark matter. Dark matter is one of those concepts that sounds like science fiction, but it is more like a placeholder name for a real effect. We observe that galaxies rotate in a way that cannot be explained by visible matter alone. Stars far from the center orbit, too fast to be held by the gravity of what we can see. Something else must be adding mass. That unseen mass behaves gravitationally, and we call it dark matter because it does not emit light in the way normal matter does. We still don't know the exact nature of dark matter. We can map its influence, we can infer its distribution, we can simulate its role in building cosmic structure. But it remains one of the universe's deep puzzles, and perhaps it is better, tonight, to let it be a calm mystery, a quiet scaffold shaping the galaxy, mostly invisible, everywhere present. If you could step far outside the Milky Way and look back, you would see a spiral disk with a central bar. You would see spiral arms traced by young, bright stars and by glowing gas clouds. You would see darker dust lanes threading through those arms. You would see the bulge shining more smoothly near the center. And you would see, if you had special eyes, the halo as a vast sphere with faint stars and clusters sprinkled through it, embedded in a larger dark matter envelope. But we are not outside, we are inside. So how do we know these things? We learn the Milky Way's shape by a mix of observation and inference. We measure distances to stars. We map gas clouds using radio astronomy. We observe how stars move and how fast. We track the distribution of elements. We study star clusters whose ages can be estimated. We use parallax, a method that uses Earth's orbit as a baseline to measure stellar distances. We use standard candles, objects whose true brightness we understand, allowing us to infer distance from apparent brightness. We also use the fact that different wavelengths of light reveal different layers of the galaxy. Visible light is easily blocked by dust. Infrared light passes through dust more easily, letting us see closer to the center. Radio waves can trace cold gas, especially neutral hydrogen, which emits at a wavelength of 21 centimeters. That radio line is one of the great gifts of nature to astronomy, because it allows us to map the galaxy's gas even in regions where dust hides everything else. In a way, studying the Milky Way is like learning the layout of a forest while standing among the trees at night. You don't see the whole forest at once. You gather clues. You listen for echoes. You measure patiently. Over time, a map emerges. Now let's move from structure to motion, because the Milky Way is always moving. The galaxy rotates. Stars orbit the center. Gas orbits too, though gas can also drift, compress, and flow along different paths. The Sun orbits the galactic center at roughly 220 kilometers per second. That's fast enough to cross a continent in under a minute. But in galactic terms, it's part of a slow, grand rotation. One orbit of the Sun around the Milky Way is often called a galactic year. It takes about 230 million Earth years, roughly. So since the Sun formed about 4.5 billion years ago, it has completed around 20 orbits of the galactic center. Not many. The galaxy's clock is slow. And as the Sun orbits, it moves through different environments. It passes near spiral arms. It encounters different densities of gas. It is influenced by the gravity of passing stars, though usually at great distances. These changes are subtle on a human timescale, but they are part of the larger story of how solar systems experience their galactic neighborhood. Within the disk, stars do not all orbit at the same speed. The inner parts rotate faster than the outer parts, a bit like the way planets closer to the Sun move faster. But the presence of dark matter changes the details. In many galaxies, rotation curves are flatter than expected, meaning that the orbital speed stays relatively high even far out in the disk. This is one of the classic lines of evidence for dark matter. In addition to rotation, stars have random motions, small velocities up and down, in and out. Over time, these motions can heat the disk, thickening it, scattering stars into slightly more varied orbits. Some of this comes from gravitational interactions with giant molecular clouds, the cold, massive clouds where stars form. Some comes from encounters with satellite galaxies and streams of matter that fall into the Milky Way. Because the Milky Way is not alone. It has companions, smaller galaxies orbiting it, like the Large Magellanic Cloud and the Small Magellanic Cloud. It also has many dwarf spheroidal galaxies, faint and diffuse, hard to see, but real. And throughout the halo, there are stellar streams, ribbons of stars that used to belong to smaller galaxies, or clusters that were torn apart by tidal forces as they fell in. This is one of the quiet truths of galaxies. They grow by eating, not in a dramatic, instant way, but over billions of years. Through mergers and accretion, the Milky Way has absorbed many smaller systems in its history, and it will continue to do so. In the far future, the Milky Way and the Andromeda Galaxy, our nearest large galactic neighbor, are expected to merge. This is not an impending catastrophe for Earth. The timescale is billions of years, and even in a merger, individual stars are so far apart that direct collisions between stars are unlikely. Galaxies are mostly empty space. The drama is gravitational. The orbits of stars are reshaped. Gas clouds compress. Star formation can surge, and the final shape may become more elliptical. But for now, tonight, we can keep Andromeda as a distant companion, a faint smudge in dark skies, and let the Milky Way remain the main stage. Now, let's talk about the raw material of the galaxy: gas and dust. Interstellar space is not completely empty. It contains gas, mostly hydrogen and helium, and trace amounts of heavier elements. It also contains dust, tiny grains of carbon and silicates, like microscopic soot and sand. Dust is a small fraction of the mass, but it has a powerful effect. It absorbs and scatters light. It helps cool gas clouds by allowing them to radiate energy. It provides surfaces for chemistry, for molecules to form, including complex organic molecules. When gas and dust gather into dense clouds, especially molecular clouds, they become the wombs of stars. Inside these clouds, regions can collapse under gravity. As a region collapses, it heats up, forming a protostar. Over time, if the core becomes hot and dense enough, nuclear fusion begins. Hydrogen, starts fusing into helium. A star is born. Star formation is not perfectly efficient. Not all the gas becomes stars. Some is blown away by stellar winds and radiation from newly formed massive stars. Some is stirred and recycled. Star formation is a feedback process. Stars form from gas, and then stars influence the gas around them. In spiral arms, gas is often compressed, increasing the rate of star formation. That's why spiral arms tend to be traced by bright, young, blue stars. These stars are massive and short-lived. They burn hot and fast, and they die in millions of years, which is a blink of an eye in cosmic time. Their presence marks where star formation happened recently. Older, redder stars are more evenly spread, and they live much longer, populating the disk and bulge as a steady background. When massive stars die, they often explode as supernovae. Supernovae are among the main ways the galaxy is enriched with heavier elements. In the aftermath, shock waves can compress nearby gas, triggering new star formation. They can also carve bubbles in the interstellar medium, large cavities of hot, tenuous gas. The Milky Way is full of such structures, overlapping, evolving, and yet, even with supernovae, the overall rhythm remains slow. The galaxy is not constantly exploding. Most stars live quietly. Most of the time, the Milky Way is a place of gentle rotation and gradual change. Now, consider the Sunday. The Sun is an ordinary star in many ways, but it is also special to us. It formed from a molecular cloud that already contained heavy elements produced by previous generations of stars. That is why the solar system has rocks, metals, and complex chemistry. Planets like Earth require elements beyond hydrogen and helium. Those elements had to be made first. So the Milky Way is not just a container for stars. It is a chemical engine. Over time, generations of stars form, live, and die. Each generation enriches the interstellar medium. The metallicity, the fraction of matter made of elements heavier than helium, increases over cosmic time, especially in the inner parts of the galaxy where star formation has been more intense. This chemical evolution matters for life, at least as we understand it. If you imagine the earliest times of the universe, there were no carbon, no oxygen, no iron. Those elements had to be produced in stars. Only after enough cycles of star birth and death could there be planets with solid surfaces, oceans, atmospheres, and the complex chemistry that biology uses. In that sense, the Milky Way is a long preparation, a slow accumulation of possibilities. Let's linger on the idea of scale again, because it is soothing in its own way. Your body is small. Your room is small. Your city is small. Your planet is small. Even the sun, enormous to us, is a single star among hundreds of billions. The Milky Way likely contains on the order of 100 billion to 400 billion stars. The exact number is uncertain because it depends on how faint stars are counted and how we model the galaxy's structure. Many stars are small, dim red dwarfs, difficult to detect over great distances. But even if we take a conservative number, the galaxy is crowded beyond imagination. And among those stars, there are planets. Exoplanet studies suggest that planets are common. Many stars host planetary systems. Some planets are small and rocky. Some are large gas giants. Some orbit close to their stars. Some orbit far out. There are planets in multi-star systems. There are planets in eccentric orbits. There are likely free-floating planets too, worlds not bound to any star, wandering through the galaxy. In the Milky Way, planetary diversity is probably vast. There is a concept sometimes called the galactic habitable zone. It is the idea that certain regions of the galaxy may be more friendly to life than others, based on factors like metallicity and radiation hazards. The inner galaxy has more heavy elements, but also more supernovae and more energetic events. The outer galaxy may be calmer, but has fewer heavy elements. The Sun's location, in the disk but not too close to the center, has sometimes been described as a comfortable middle distance. This concept is not settled. and life may be more resilient than we assume. But it is a gentle reminder that even within a galaxy, environments vary. The Milky Way is not uniform. It has neighborhoods. Now, let's drift toward the galactic center again, but softly, as if moving through a slow zoom. The center of the Milky Way is hidden from our eyes in visible light by thick dust in the disk. But in infrared and radio, we can see through. We can observe stars orbiting something compact and massive. Those orbits reveal the presence of Sagittarius A star. Astronomers have watched stars near the center complete their orbits over decades, measuring their paths precisely. From that motion, we infer the mass and compactness of the central object. The evidence points strongly to a supermassive black hole. Around the center, there are also dense star populations, including old stars and regions of active star formation. There are magnetic filaments. There are energetic phenomena like outflows and bubbles, large structures extending above and below the galactic plane. Some of these features suggest that the galactic center had more active periods in the past, perhaps with the black hole accreting more material, shining more strongly. Our galaxy's central black hole is relatively quiet compared to those in active galactic nuclei, where black holes are feeding rapidly and producing brilliant radiation. Sagittarius A star is more like a sleeping giant. It occasionally flares, but it is not blazing constantly. In an odd way, that feels fitting for a sleep channel. Even the galaxy's central black hole, in our era, is calm. Now let's return outward to the spiral arms and the pattern of star formation. If you could see the Milky Way in ultraviolet light, you would see bright regions where hot young stars live. If you could see it in far infrared, you would see the glow of warm dust heated by those stars. In radio, you would see the distribution of neutral hydrogen extending beyond the visible disk. The gas disk is larger than the stellar disk. Hydrogen stretches farther out, like a faint, extended envelope. This extended gas is part of how galaxies keep forming stars. Over time, star formation uses up cold gas, but galaxies can replenish gas through accretion from the intergalactic medium and through mergers. The Milky Way is still forming stars today. It produces on the order of 1 to a few solar masses of stars per year, roughly. Compared to some starburst galaxies, that is modest, but it is steady. Star formation tends to occur in clusters. Many stars are born in groups, in nurseries, where hundreds or thousands of stars form from the same cloud. Over time, those clusters can disperse. The stars drift apart, becoming part of the general disk population. The Sun itself likely formed in such a cluster, alongside siblings that have long since scattered across the galaxy. Some clusters survive longer. Globular clusters are ancient, dense groups of stars, often containing hundreds of thousands of stars. They orbit in the halo and bulge. Many globular clusters are extremely old, formed early in the galaxy's history. They are like fossils, preserving information about the conditions of the early Milky Way. If you imagine the galaxy's history, globular clusters are among the earliest chapters. The disk and spiral structure came later, as gas settled into a rotating plane, forming stars over long periods. Now, let's talk gently about time. The universe is about 13.8 billion years old. The Milky Way formed early, perhaps within the first billion years, through the merging of smaller structures and the accumulation of gas. The early galaxy was likely more chaotic, with more frequent mergers. Over time, it became more settled, building a disk. The oldest stars in the Milky Way are very old indeed, with ages over 13 billion years in some estimates. These stars are low in heavy elements because they formed before the interstellar medium was enriched. They are rare and faint, but they exist, especially in the halo. As the galaxy evolved, star formation continued. Different regions formed stars at different rates. The inner regions enriched faster. The disk built up. Spiral structure emerged. The Sun formed much later, about 4.5 billion years ago, when the galaxy had already been around for a long time. That means the Milky Way had already lived through many cycles of star birth and death before our solar system appeared. Earth is not an early planet in cosmic history. In many ways, it is a mid-era planet, formed after the universe had time to create a rich periodic table. This is comforting if you think about continuity. The galaxy was doing what it does long before we arrived, and it will continue long after. Our lives are brief, but we exist within a stable, long-running process. Now, consider what it means to locate ourselves in the galaxy, physically and scientifically. We measure our distance to the center. We measure the galaxy's rotation. We map the spiral arms. We catalog stars. We model the distribution of mass. We build surveys that scan the sky and record billions of objects. Modern astronomy is, in part, the art of turning faint light into structured knowledge. One of the most important modern projects has been the Gaia mission, which measures positions and motions of stars with extraordinary precision. With Gaia data, astronomers can build a three-dimensional map of a large portion of the Milky Way, including stellar distances, velocities, and motions. This allows us to see streams, resonances, waves in the disk, and the footprints of past interactions. In the disk, there are ripples, like the surface of a pond disturbed by a passing object. Some of these ripples may come from the gravitational influence of satellite galaxies. The Milky Way is not a perfectly smooth disk. It has warps and bends. Its outer disk is warped, like a vinyl record slightly bent at the edge. This warp may be caused by interactions with nearby galaxies and by the gravitational pull of the dark matter halo. It's easy to imagine a galaxy as a neat, static diagram, but the real Milky Way is a dynamic, imperfect system, always responding to gravity, always slowly rearranging. Even our local region has structure. The sun sits inside what is sometimes called the local bubble, a cavity in the interstellar medium filled with hot, low-density gas. This bubble may have been carved by supernovae in the past, perhaps tens of millions of years ago. The local bubble is not something you can feel. It is not like weather. It is just a large-scale property of the interstellar environment, another reminder that space has texture. Now, let's take a moment to imagine what the night sky is really showing you. When you look at a bright star, you are seeing a point of light that traveled through space for years, decades, centuries, depending on the star's distance. The nearest star system, Alpha Centauri, is about 4.3 light-years away. Many of the bright stars in the sky are tens or hundreds of light-years away. Some are thousands. The Milky Way band contains light from stars across much larger distances. So, the night sky is a mosaic of different times. The light from each star began its journey at a different moment. The sky is a quiet time machine. Not in a dramatic way, in a gentle way. And when you see the Milky Way band, you are seeing the integrated glow of billions of stars, plus the shading of dust. You are seeing the disk from the inside, a reminder that we are embedded in something vast. Now, let's bring in a subtle piece of physics, the way gravity holds galaxies together. Gravity is the architect here. It is the long-range force that shapes orbits, pulls gas into clouds, builds stars, and maintains the galaxy's structure. In the simplest picture, stars orbit because they are in free fall around the combined mass of everything inside their orbit. They are always falling toward the center, but their sideways motion keeps them in orbit. In a disk galaxy like the Milky Way, most stars follow roughly circular orbits, though not perfectly. Over time, encounters and resonances can change orbits. Spiral arms can exchange angular momentum with stars. The central bar can also redistribute angular momentum, driving gas inward, feeding central star formation, and influencing the overall structure. Bars are interesting. They are common in disk galaxies. They form naturally in simulations as disks evolve. A bar is like a rotating gravitational pattern that can trap stars in elongated orbits. It can also act like a channel for gas, guiding it inward, which can influence the galaxy's central regions. The Milky Way's bar is not something we can easily see directly, but multiple lines of evidence support its existence. If you imagine the galaxy as a living system, the bar is part of its metabolism, slowly moving matter and energy around. Now, a soft note about dust again. Dust is why the Milky Way looks mottled. Dust is why the center is obscured. Dust is why infrared astronomy is so important. But dust is also why the galaxy is fertile. Without dust, gas would have a harder time cooling and forming stars. Dust grains allow molecules to form. They are the quiet chemistry labs of space. And among the molecules in interstellar clouds, astronomers have found many complex organic molecules. Space chemistry is surprisingly rich. The cold, dark clouds where stars form can contain alcohols, acids, and a variety of carbon-based molecules. This does not mean life is there, but it means the ingredients for complex chemistry can arise naturally, under the right conditions, across the galaxy. So when we speak of the Milky Way as a place where planets form, we are also speaking of a place where chemistry is always at work, quietly building complexity. Now, let's gently zoom out again to place the Milky Way in its larger context. The Milky Way is part of a small group of galaxies called the Local Group. The two largest members are the Milky Way and Andromeda. There is also the Triangulum Galaxy and many smaller dwarf galaxies. The Local Group itself is part of a larger structure within the Virgo supercluster region, part of the cosmic web. The cosmic web is the large-scale distribution of matter in the universe. Galaxies are not sprinkled randomly. They form along filaments of dark matter and gas, like nodes in a vast network. Between filaments are voids, large regions with fewer galaxies. The Milky Way sits within this web, shaped by it and contributing to it. This can feel abstract, but it can also feel calming. It reminds you that the universe has structure on every scale, from dust grains to star clusters, from galaxies to clusters of galaxies, from filaments to superclusters. Patterns repeating, complexity arising from simple forces. Now, back to something more immediate. What would it be like to travel through the Milky Way? In practice, interstellar travel is extremely difficult. Distances are too vast. Even the nearest stars are far beyond our current technology for fast travel. But as an imagination exercise, it can be soothing. Imagine leaving the sun and traveling outward through the disk. You would pass stars with different colors: red dwarfs, orange stars, sun-like stars, white stars, blue giants. You would pass planetary systems you could never fully explore. You would pass nebulae, glowing clouds where stars are born. You would pass dark clouds, dense with dust. If you moved toward the inner galaxy, the star density would increase. The sky would become more crowded. The background would brighten. You would encounter regions with more intense star formation, more supernova remnants, more energetic phenomena. If you moved outward toward the edge of the disk, the star density would decrease. The spiral structure would thin. The gas would extend farther. The night sky might become darker, emptier, more sparse. Beyond the disk, the halo would surround you, with its faint stars and globular clusters. And beyond that, intergalactic space, a vast darkness with occasional galaxies like islands. The Milky Way's disk is thin compared to its width. If you imagine the disk as a plate 100,000 light-years wide, its thickness might be only a few thousand light-years for the thin disk, and perhaps several thousand more for the thick disk. So, it is like a wide, thin city of stars, embedded in a much larger dark matter region. Now, let's return to the human experience of the Milky Way, because this is a sleep script, and the human mind likes anchors. For most of human history, the Milky Way was a mystery. Cultures around the world noticed the band of light and told stories about it. Rivers, roads, bridges, milk, spirits, ancestors. The name Milky Way itself comes from the idea of spilled milk. In Greek mythology, it was linked to Hera. In other cultures, it had different meanings. What is striking is that nearly everywhere, people looked up and recognized it as something distinct, something worth naming. Science later revealed that this band is the disk of our own galaxy. That realization is one of the most profound shifts in perspective. The Milky Way is not a feature painted on the sky. It is the structure we live inside. The understanding came gradually. Telescopes revealed that the Milky Band resolves into stars. Then astronomers tried to map the distribution of those stars. At first, it was difficult because dust obscures our view. The true center was not obvious. Over time, infrared and radio observations filled in the hidden parts. Today we have a far more accurate picture, but it is still incomplete. We are still learning about the bar's shape. We are still mapping the spiral arms. We are still discovering faint dwarf galaxies. We are still debating details of the dark matter distribution. We are still uncovering the galaxy's merger history, reading it from stellar motions and chemical fingerprints. So the Milky Way is both known and unknown. It is familiar in outline, mysterious in detail. That's a pleasant balance for the mind. Enough structure to feel grounded, enough mystery to feel wonder. Now, a gentle thought about the sun's long-term future within the galaxy. The sun will continue its orbit around the galactic center. It will pass through different regions, but on the timescale of the sun's life, the galaxy will also change. Spiral arms may shift. The bar may evolve. The Milky Way may accrete more dwarf galaxies. The Large Magellanic Cloud may interact more strongly, stirring the disk. And far in the future, the merger with Andromeda will reshape everything. The night sky would change dramatically over millions of years as Andromeda grows larger, as tidal streams stretch across the sky, as star formation episodes occur. The final merged galaxy might be an elliptical-like system, sometimes nicknamed Milkomeda. But all of that is unimaginably far away. On the timescale of a human life, the Milky Way is steady. The stars keep their positions relative to each other. The band of light stays where it is. The galaxy is a stable background, a quiet cosmic architecture above the sleeping Earth. Now, consider another aspect, the light pollution of modern life. In many places, the Milky Way is invisible. City lights brighten the sky, washing out faint starlight. This is a loss in one sense, because it disconnects us from the natural night. But it is also a reminder. The Milky Way is always there, whether you see it or not. It is above clouds. It is above streetlights. It is above the atmosphere. The galaxy does not vanish when it is hidden. It simply becomes harder for our eyes to detect. If you like, you can imagine it now, even if you cannot see it from where you are. A soft arch across the sky, a quiet river of starlight, dust lanes like shadows, star clouds like mist, all of it steady and real. Now, let's slow down even more and rest on a few simple images, each grounded in science, but allowed to be gentle. First image. A spiral arm is a region of slightly higher density, where gas compresses and where new stars form in clusters. Bright blue stars lighting up their birthplaces, dust absorbing light and re-radiating it in infrared. Second image. The sun orbiting the center, carrying the planets with it like a small lantern moving around a vast city. One galactic year taking hundreds of millions of Earth years. Third image. A halo of old stars and globular clusters surrounding the disk, embedded in an unseen dark matter structure that quietly holds everything together. Fourth image. The galactic center, hidden behind dust, containing a supermassive black hole, not aggressively feeding, mostly calm, with stars swirling around it in tight orbits. Fifth image. Interstellar dust grains, tiny, cold, and essential, allowing molecules to form and clouds to cool, enabling the next generation of stars. These images are not separate. They are parts of one system. Gravity shapes the whole. Time deepens it. Chemistry enriches it. Now, if the mind wants a final point of calm, it can be this. The Milky Way is not rushing. It is not anxious. It is not trying to arrive somewhere quickly. It is simply evolving under the laws of physics. It has been doing so for billions of years. It will continue for billions more. And in that slow, steady process, there is room for small lives to exist, to wonder, to rest. So as you listen, you can let the galaxy be what it is: a vast, rotating disk of stars and clouds, a central bar and bulge, a halo and dark matter scaffold, a chemistry engine, a history of mergers, a home for planetary systems, a faint band of light across the night sky. You don't have to hold the entire structure in your mind. You can let it be a background presence, like a low, steady hum, a spiral shape, turning slowly, a quiet center, a wide disk, a gentle river of starlight, and you, here on a small planet, in a calm room, listening, breathing, letting the day loosen its grip. The Milky Way continues overhead, patient and vast, while the Earth turns and night deepens and sleep becomes easy.